we are only going to cover through section 8.7. 8.8 and following, we're not going to be covered in the lecture, no videos, and will not be on the exams. Okay, so just make a note of that to yourself. Quantum numbers we were talking about in class last time, and the relationship to shapes of atoms, where the electrons are. I'm going to quickly cover that in this video. Then we're going to talk mostly in the first video about electron configurations of atoms and ions, and the structure of the periodic table, like how it gets its shape, where that comes from. It has to completely to do with these quantum numbers. We're also going to talk about energy level diagrams of hydrogen and multi-electron systems, which means every other element on the periodic table. And then the next video is going to deal with 3 periodic trends. That'll be a kind of a quick, it'll be a shorter video than this one is. All right, so let's jump to just a quick review. In class last time, we showed you some model kits. One of your classmates tried to destroy them, and I passed around s orbitals, p orbitals, d orbitals, f orbitals, which were 3D printed. And if you remember, the L value tells us what type of orbital it is. So if L is equal to, actually we need another one in here, we need a 0. If L is equal to 0, we call this an s orbital, 1 is a p, 2 is a d, 3 is an f, 4 is a g, etc. S orbitals, if you recall, have a spherical shape. P orbitals have kind of a dumbbell shape with 1 node. D orbitals look more like a cloverleaf kind of shape. They've got 2 lobes. And F orbitals have 3 nodes. Gets a little bit harder to draw in 2 dimensions. They get more complicated. G orbitals are going to have 4 lobes. They're going to even be more complicated. The other thing we mentioned is as the principal quantum number n, so this is n equal to 1, 2, 3, as the principal quantum number goes larger, the n values, or excuse me, the size of the orbitals get larger. So the n number is telling us about the size of a set of orbitals. The L number tells us about the shape of the orbitals, and the m sub L value tells us about the orientation in space. Now for an s orbital, there's only one type of s orbital, but for a p orbital, L is equal to 1, and the ranges are -1, 0, and +1. So there's actually 3 different p orbitals. That's what's illustrated here. Now, can we assign the -1 to the x-axis and the 0 to the y-axis and the +1 to the z-axis? Yeah, you can, but it's arbitrary. It doesn't really matter which one gets assigned to which. The important thing is that there are 3 p orbitals. And then when we go to d orbitals, L is equal to 2, which means m sub L is equal to -2, -1, 0, +1, and +2. So there's 5 d orbitals. That's what's drawn here. 1, 2, 3, 4, 5 different shapes. 5 cloverleaf kind of shapes, except there's one funky one with a ring in the middle. Okay, but most of them look like 5 cloverleaf shapes oriented differently in space. Now the last point I want to make as a sort of reminder to you, this drawing is called the boundary surface, which is showing you this is where the electron will be 90% of the time. It will be within the perimeter of this boundary space. Okay? Could the electron be outside here? Sure. For 10% of the time it could be outside of there, but 90% of the time we draw it inside of this, or that we say the electron is inside of this sphere. Okay? And that tells us the shape of the orbitals, and later on when you get to organic chemistry, that's important because the shape of the orbitals is where the electrons are. That's where the chemical reactions are going to take place.